Okay, welcome to this video on the 2013 question B3. So it's a mix of perspective and skewed lines. So the Egyptian pyramids shown in a 3D graphic are considered to be architectural masterpieces. They're square based, built in precision terms of alignment, geometrical shape and proportion. Figure B3 shows the planned elevation of a square based pyramid with an intersecting triangular entrance. Part A, draw the given plan and elevation. Okay, that's very important to note, the way it says elevation, and construct a perspective drawing of the structure given the following. The spectator is 8 meters from corner A, the picture plane is touching corner A, the horizon line is 5 meters above the ground line. Use an auxiliary vanishing point to locate the sloping edges of the entrance. Now, one thing we do not know is that distance in how far back that is in plan. Right, so I'm going to get started drawing this. The scale is 1:100, so convert everything into millimeters and divide by 100. So 8 meters equals 8,000 millimeters, and divide by 100, you knock 2 noughts off, you get 80. So I'm going to draw in my XY line. Okay, mark 80 along the bottom, then 20 and 20 from either side. Okay, then I'm going to go up 80 to the middle then. For the apex, so up 80. Then the sloping lines have, the sloping entrances are at an angle of 40 degrees. So I can use my protractor, they're at an angle of 40 degrees. Then I'll construct my plan view. I'm going to drop down 5. It's a square base, so it's 80. So I'm going to heavy that in tightly there, so I'll need it later. The entrance sticks out 10 mil. This is the entrance of the pyramid. Entrance there sticks out 10 mil. So I'm going to drop down 10, drop these down, can heavy that in, heavy this in. Now, as I said, I'm not sure how far back it goes, so I'm going to use the concept of parallel lines. Okay, or parallel in every orthographic view. So if I draw a line right through the apex of the slope and entrance and elevation, it touches the two side edges here. In plan, I'm going to find them by joining the corners. Okay, now I'm going to drop these two corners in elevation until they hit their respective lines here in plan, and that will get me the answer. So if I drop that line there, and this one, look, this line and the base are parallel in elevation, so this baseline and this line are parallel in plan, and they contain the point of intersection. So I can join them back together. And there's the plan and elevation complete. Right, now the next part of the question, it says, okay, the spectator is 8 meters from corner A along a 60-degree line. So here's corner A, so 60 degrees. 80 mil. So here's the spectator. We're going to join our spectator to the two outermost points of the object. We're going to get our compass now and we're going to bisect the angle. So I just need to change that angle just a tad. So the bigger the radius, the better. So there's the bisector. Now the picture plane is perpendicular to the bisector. So I'm going to just use my sliding set square won't have enough room, so my adjustable set square rather won't have enough room. So sliding set squares, or sliding set square and t-square, there's the picture plane, there's the horizon line. The horizon line is 50 millimeters above the ground line, so I'm going to mark 50 there. Here's the ground line. Fix that slightly. And here's the ground line. Now, then we need to get the vanishing points. So I'm going to go parallel to one set of lines from S. I'm going to go parallel to these from S. So line across here. Okay, line up from S parallel to these ones. Okay, until they hit the picture plane, and I can extend this until it's the picture plane. There we go. Right, then down perpendicular to those to the picture plane from those points. Okay, is the key thing. So here's a vanishing point here. Okay, then here's a vanishing point over here. So there we go. So I can label them VP1, VP1, VP2, VP2. Right, so corner A is on the picture plane, so I'm going to bring corner A down perpendicular to the picture plane. So there we have point A. Right, so I can join A to VP2 and VP1. So A to VP2 and VP1. Now, if I want to get where the corner of the pyramid is, I find in perspective, I find it in plan. Okay, I join it to the spectator which is already done. I bring it down perpendicular here. So there's the corner of the pyramid. Right, I can heavy that in. I'll heavy them in even darker now in a moment. So then I'm going to do the opposite side. So I'm going to find where this point is joined to the spectator, bring it down when it's perpendicular. So there we go on the pyramid. Now I'm going to pause and just heavy one line in. Of that done there. Now only true heights can be applied along a point on the picture plane. So if I want to get the apex, right, I can extend a line from the apex through until it hits the picture plane in plan. Now I'm going to go down perpendicular to the picture plane from this line. Okay, and I go where it hits the ground line, I'm going to mark up 80 from that. So I'm going to mark up 80 from that. Now I have to join this back to VP2 as that line is parallel to VP2. So I have to join it back to VP2. Now, somewhere along this line lies the apex. So if I want to get the apex exactly, I join the apex to S, down perpendicular to the picture plane until it hits the point. Now I can join the apex AP to this point here and this point here, and then I can join it to this point here as well. Right, now I want to do the slope and surfaces. Okay, the entrance is what I want to do. So here's the start points of the slope, the entrance. So I'm going to join them test. I don't have to join them all the way. Okay, now where they hit the picture plane, I'm going to bring them down perpendicular to it, as I've said many a time. So that's them there and there. Now, so they go to VP2, so I'm going to draw a line from VP2 out through them. Okay, and I can join this point to S now. Don't have to bring it all the way. I'm going to go down perpendicular to it now until it hits here. So I can heavy in the line there. I can join it to VP1. And now I'm ready to do the slope and surfaces for the edge. Right, the angle of the slope is 40 degrees. The slope and entrance is here in plan. So the auxiliary vanishing point is going to be above VP1, because if it was horizontal, it go to VP1. So I have to measure an angle of 40 degrees from S to VP1. So I'm going to measure this angle of 40 degrees from S to VP1. Now that, I'll just check, does that look right? Yes, it does. So I can go straight up here. Now, that's the true height. So I'm just going to extend that on. I'm going to take the height of it here. So I'm going to take that height, step it above VP1. So I'm going to join the slope and surface up to here. Now, to figure out where exactly it stops, I'm going to join this point to S, and then where it hits the picture plane, down perpendicular as we know. And then we can heavy that in, heavy it in here. We can join back to VP2. Now, this point doesn't join to the auxiliary vanishing point as it's at a different angle. So I can join this corner to S, and then where it hits the picture plane, down perpendicular to it. And then there we can heavy in there. Okay, and I'm going to pause and heavy in my pen, and then I'll deal with part 2 of the question. So there's it heavied in. Now I'm going to start on part B. So I'm just going to move this over. Okay, on a separate diagram we have to deal with some skewed lines. So I'm going to draw in a Y line and an XY line. Okay, so the coordinates, right? The A coordinates are how far you go across from the YY line, the N vertical plane. The Y coordinates, okay, are how far you go up from the XY line or the horizontal plane, and the Z coordinates are how far out from the vertical plane you go, or how far down from the XY line. So it's A, B and C, D. We have two such passageways are represented by A, B and C, D. The horizontal and vertical coordinates of these skewed lines are given below. So I'm going to pause the video and plot these out, and I'll quickly recap on how I got them when I reopen the video. So we have the skewed lines drawn. So just a reminder, to get A, so I went over the X coordinate, okay, from the YY line, the N vertical plane. I went up 30 the Y coordinate, so from the horizontal plane, and then out 20 from the vertical plane. The XY line is the VP in plan, so down 20. Now, so we have the skewed lines A and B and C and D drawn. Okay, determine and indicate in millimeters on your drawing the true length of the shortest connecting shaft that can be drilled between the two passageways A, B and C, D. So basically the shortest perpendicular distance. So how we're going to do this? Right, from D we're going to draw a line parallel to the XY line. Okay, and then from A we're going to draw a line parallel to line AB. Okay, so I'm going to draw a line parallel to AB from C. Okay, now I'm going to call this point P. Now I need to find point P in plan. So I'm going to drop P straight down. And, ooh, nasty. Parallel lines are parallel in every orthographic view. So if I went parallel to AB from C, I must do the same in elevation, I must do the same in plan. So I'm going to go parallel to AB from CD, or from C in plan. So I'll do that now. So parallel to AB from C in plan. Now here's point P. So I join P back to D. Now this is a true length. So I'm going to look along the true length of this line because I want the triangular surface to appear as an edge. Alright, and the purpose of doing this construction in elevation is if this triangular surface will be parallel to line AB if line C to B is parallel to AB. Now when you look along line P to D, you'll get the triangular surface appearing as an edge, and line AB will be parallel to the edge of the surface. But line AB and CD will appear parallel here, but they'll never actually be parallel. So I'm projecting along P to D. So there's my points. I can draw in my X1, Y1 line. So I just carry on these points. Okay, now I can take my heights from elevation. There's clearly a lot of height to be covered, so I can use a datum line to reduce the distance. So I'm going to take the height of A. I'm going to lift, find A, mark it in here. I'm going to take the height of D. I'm going to find D, mark it along here. B is the same height, so I can mark B there. P is the same height as well, it's already done. Then I can get the height of C. I can find C here and mark it in. Right, so I'll label the points. Right, that's A, that's B, this is C, and this is P/D. Now those points are parallel. Okay, if they don't look parallel, then I need to fix something. Okay, they're pretty good now. So there. So there they are. There's the two skewed lines. Now, the shortest perpendicular distance can be found looking at a right angle to those two lines. So I'm going to look perpendicular to them. So I'm going to project down along here. Here's the x2, y2 line. I can take my distances from my x1, y1 line back, or use a datum if needs be. So I'm going to take this distance here, mark it there. B, take it there, mark B. Okay, D, I'm going to take the distance there, D, mark it here, and then C, I want to take the distance and mark it back for C. So there's C2, A2, okay, that's D2, that's B2. So the lines join together. Now, the point of crossover, that's the shortest perpendicular distance, okay, between the lines. So I project that back to here. Okay, it says determine and indicate in millimeters the true length, so I measure that there, it's 44 millimeters. Okay, now it doesn't say determine the projections, but it'd be safer to do so to complete the elevation and plan in that projecting shaft. So I'm going to bring this back to AB and bring this back to CD. Okay, then they can be joined in plan, and then to find them in elevation, we obviously just bring them straight up. So there it is there on it. There it's on CD. That's the elevation of the shortest perpendicular distance. Right. So that's the question done. Cheers. Thank you. Bye bye.